Hello.
Yeah,
So,
but we have also stream
okay.
on YouTube, so
So I'll have to hold it.
people,
I have to hold it all the time.
that would be great.
In SciPy, they gave me a collar mic. So. Right. Okay. Yeah. So just a request. I have already pasted the link and the link to the GitHub repo and the the data sets on the registration help channel. You can download the data set and clone this repo at your end.
I also copied it into room 2.1 information if you can access it into places. Okay.
So we'll have first initial 5 to 10 minutes just for downloading and setting up the environment. And if you face any issues, please let me know.
If there will be any important questions that you are answering to the microphone, you can repeat them or we can ask you.
Yeah, sure.
But you can just repeat.
Sure, sure, sure. Sure. So you can clone this repo, the link of which is already given on the registration help channel, and as well as I have put the data sets, the link of the data sets here. You can download this S1A GRDH dataset and the shivamoga.zip dataset. So in total, combining them, the total size is 2 GB. And if you face any issue, please let me know. So I have streamlined it using Pixie. So Pixie is fair easy to download and go ahead. You can install Pixie through PowerShell, or you can download it from the installation. It'll take a few minutes. So we'll roughly start at 2:10 by the time everyone is done with the installation and everything. Yeah, I've already shared on the repo. The link is already shared on the repo. Yeah, so you can download this S1A, this one, and the other one is shivamoga.zip. These two needs to be downloaded. So in the Discord, I have already mentioned the names of the two datasets also. So this one and this one. In the registration help channel, I have already posted. Yeah. Because I didn't have access to other channels, so I posted it there only. Any issues in downloading or cloning the repo? Very slow. That's why I tried to share it earlier, but it will take some time probably.
After the tutorial, we have closing talk. So for 10 minutes.
Maybe data sets are a little bit heavy.
Yeah. And the Wi-Fi isn't perfect.
Yeah.
As usual.
I hope the repo is cloned by everyone. Yeah. The data sets we can keep on parallel, and I'll start in 1 minute.
How I can set up the environment with Pixie?
You just have to clone this repo, and just you have to install Pixie from probably from there, from the website.
Oh, okay.
Yeah.
And then I have to run it?
Yeah, you have to just go to the repo.
And this Pixie run that you mentioned
Yeah,
here?
Pixie Run Lab.
Okay, thanks.
So Pixie install won't take much time.
Yeah.
Once you have cloned the repo, we go inside it and we just run Pixie Run Lab, and we can get a. We go to the notebooks, and inside notebook we launch this Intro to Microwave RS. So, good afternoon, everyone. Let's start with the workshop on microwave image processing, exploring SAR images from foundations to frontiers through Python. So this is a workshop that I'm delivering that takes you from the basics of synthetic aperture radar, specifically from spaceborne radar's point of view, and how to deal with these images through Python. So it's just a primer tutorial that gives you an idea how to deal with these images and what is the physical significance of these images. So I'm Shubham Sharma. I'm working as a senior data scientist at Endor Tech India Private Limited in Bangalore. And I've been working at the intersection of SAR image processing, remote sensing, and computer vision for the past 10 years. And it's really a great feeling when you apply Python programming to solve some of the key aspects of image processing. So let's start with the session. I think you can keep the data sets in download parallelly. And so the key things that we are going to discuss today is some theory, because the theoretical basics are needed to understand such kind of imagery. So we'll be discussing key foundations, SAR geometry, how a radar sees the ground. So basically SAR is nothing but a radar that is imaging the earth in the electromagnetic spectrum, specifically the microwave region of electromagnetic spectrum. So we'll discuss some key aspects about polarization, image formation, opening data with GDAL, NumPy with SAR arrays, and some visualization and reading the metadata. That's it in the first session. And then we'll go ahead with some calibration and speckle filtering stuff, and then with a simple application. So I'll try to wrap it up within 1.5 hours, although the topic is quite huge and difficult to be covered within such a small timeline. Although I have delivered it within 4 hours at SciPy, so I'll try to wrap it up within 1.5 hours. So yeah, let's start. What is remote sensing? So remote sensing is basically sensing some properties of a target. That target can be anything, and which is located at a distance from the sensor. So the sensor is basically not in contact with the target, but quite a lot of distance away from the target, and we try to measure its properties. So remote sensing as a whole deals with such kind of the core idea behind remote sensing is that. And through this remote sensing, we can monitor vital aspects on Earth's surface, wherein many sensors go into space and try to image Earth in various regions of electromagnetic spectrum. And each region has its own property and its susceptibility to a particular target on the Earth's surface. And hence, the sensor that works in a particular frequency band or a wavelength monitors that specific properties of the target. So we have, namely in the field of remote sensing, we had optical sensors as well as the microwave sensors. So basically, optical sensors are those which image Earth in the visible range of electromagnetic spectrum. So that is VIBGYOR, 400 to 700 nanometers. And microwave region is totally different, which totally captures the images of Earth in the microwave region, which goes from 300, 500 megahertz to 8 gigahertz. Normally, the remote sensing sensors, the microwave sensors fall in this range. So basically, as you can see here, the shorter wavelength, higher frequency, higher energy, and longer wavelength, lower frequency, lower energy. So if we see the electromagnetic spectrum, we see that the radio frequencies are from 10 to the power 4 meter to 1 meter. Microwaves wavelength ranges from 10 to the power minus 3 meter to 1 meter. And there, as we go with smaller wavelengths, we go with the visible and infrared light. So basically, the microwave region, in the microwave region of spectrum, the sensors that operate, or the sensors that we are going to talk about, the images that we are going to talk about, are mainly in P, L, S, C, and X bands. So basically, you can see the X band, which goes from 8 to 12 gigahertz. You have C band, which goes from 4 to 8 gigahertz. S band from 2 to 4 gigahertz. L band from 1 to 2, and P band from 300 megahertz to 1 gigahertz. Each band in which the sensor operates has its own capability and its functionality to view features in that particular range. So X band, if you want to target higher resolution, so basically for military applications or for specific building monitoring and target detection, the X band is quite good. And many SAR sensors, radar sensors that work in this area of the spectrum, mainly TerraSAR X, which is a satellite, which is a SAR sensor developed by DLR of Germany. And C band is 4 to 8 gigahertz. So in this band is known as the compromise band between L and X band. So basically, this band is quite susceptible for all the kind of applications such as agriculture and, in case of forestry applications. A lot of applications find their place in the C band. And then we go with S band. S band also has similar applications in agriculture, forestry. L band with as we go down the line, the wavelength increases and the frequency decreases. So P, L, and S band are quite good for monitoring forestry-based applications, wherein the penetration of microwave increases. So by penetration, we mean the penetration of the forest canopy. So if we want to measure lower parts of the canopy, we need to go with higher bands of SAR. So P band has in P band uh, there are SAR missions, namely Biomass by ESA, European Space Agency, and L and S band recently launched NISAR works in L and S band. So basically, you get for a particular area 2 images, one in L band and one in S band. And C band is where Sentinel-1 works, which is also a sensor by ESA. And we are going to analyze the Sentinel-1 images. So this was a little bit primer about the microwaves and their bands. So what does SAR offer? So basically SAR is a side-looking radar. So if you know about a normal radar just transmits the microwave pulses and they come back. So due to this time delay, the radar just measures the distance to an object which is moving or might be stationary. So due to this, the radar just tells you what the velocity or at what position the target is available. But in the case of SAR, the SAR is a moving radar. So it moves with the platform and it looks sideways, either right or left. So it's not imaging in the forward direction. It's mounted on a sensor that is moving with certain speed in a particular direction, which is called as the along track direction that I'm going to show. And it images in the cross track direction. So the cross track direction is, you can see it as a 90-degree or at some angle perpendicular, at some angle to the along track direction, which is known as the cross track direction. So it's a side-looking airborne radar, or it can be spaceborne. So it mainly depends on the platform in which it is mounted. It can be mounted on drones, or it can be mounted on our aircrafts, or on the satellite. So let's discuss what is the difference between radar versus the real aperture radar and the synthetic aperture radar. So the radar in general detects and range targets. So basically it will just give you the position of the target. Then real aperture radar is used for imaging. So real aperture radar is also used for imaging. And synthetic aperture radar is used for high resolution imaging. So in this radar, the azimuth resolution. So basically by what I mean by azimuth resolution, the direction in which the radar is moving, that is called as the azimuth, and the direction in which it images is called as the range. So you get an image in the azimuth cross range. So your 2D image that is created, the y-axis that you normally see in the image is called as azimuth, and the direction in which it images is called as the range, is the x direction. So in real aperture radar, the resolution, so there is a key term called as resolution. By resolution, we mean that we should be able to image two objects on the ground at a particular distance. So basically, if two objects, if I say that a sensor has a resolution of 2 meters, that means on ground, these two targets were separated by 2 meters and they will be clearly visible on the image. So that means the image has a resolution of 2 meters. So if I say that it is 0.5 meter, that means it has a very high resolution. The two targets which are separated on the ground by 0.5 meter, they will be visible. So, but in the case of real aperture radar, its resolution is a function of r lambda by L, where r is the height of the sensor, distance of the target to the sensor, and lambda is the wavelength, and L is the length of the antenna. Now, to get such kind of higher resolution on ground, you need a higher length of the antenna, which is capital L, as given by the formula. But in the case of, so it is totally impractical to have a very high length of the antenna, due to which the resolution requirements become very tough. So in order to get the same resolution and with the same length of the antenna, the movement of the platform basically helps us in synthesizing the length of the antenna. That's why it is called as synthetic aperture radar. So the uh, a, a SAR antenna having a length L, when it moves by distance 2L, by the time the microwave pulses, when they have hit the ground, and by the time they have come up, they are received back to the sensor, the 2L distance has been covered. So basically, the resolution of synthetic aperture radar is L by 2. That is the length of the antenna by 2. Hence, synthetic aperture radar can deliver the same resolution of image with the same length of the antenna, wherein you need not make uh, a new antenna with a higher length L, and you can get the good resolution of image. So hence, we use synthetic aperture radar, and we do not need to give a, we do not need to have a higher length of the antenna for imaging. So let's go to the key foundations. So this is an active sensor. By active means it transmits its own microwave pulses and it does not depend on any secondary source. Now, as I have already discussed that there are visible and the microwave region of spectrum, the images that you see in the visible region of spectrum are optical images that you normally see in the Google Maps. They are the normal Google Maps images that you see, which normally have RGB channels, and you see them very fancy and you can make out the features on the earth. So it's normally more than one channel. The SAR images are single channel images, that is grayscale images. But the key difference between the two sensors is it allows for 365 days, 24/7 monitoring of any target on Earth, and it can work in any kind of weather. So all weather capability is being given by the SAR sensors, not the visible sensors that you see uh, in on Google Maps, which work in the optical domain. So right now, like rain is going on, and the clouds are there. So in the case of visible region of spectrum images, the optical images, you'll see clouds on the image, and it's very difficult to remove those clouds. But SAR has the capability to penetrate the clouds. So you can see the image 24/7, 365 days as a normal image, and they can penetrate the clouds. The microwaves can penetrate the clouds, and you can easily make out what features are there. So I have discussed this, and let's just discuss the geometry in which the SAR does the acquisition. So as I discussed orally, right now we can see visibly this is the along track direction in which the sensor moves, and it has a length L. The SAR sensor has the length of the antenna as L, and it subtends an angle on the ground. This angle is known as the look angle, which is the angle between the perpendicular to the nadir. Nadir is the lowest point on the earth, and this angle is called as look angle of the sensor. And the point at where it subtends that angle, the angle with the perpendicular is known as the incidence angle. So incidence angle is quite a key aspect when we do these kind of we analyze these kind of images. So you can see that this is the whole part which is being illuminated by the beam on the ground. So this part is called as the swath. This whole part is called as a swath, and this is the swath width. Now, if we see in a normal 2D structure, this is the sensor, and we see this is look angle, this is the depression angle, this is the incidence angle, and this is the grazing angle. So the incidence angle changes from the point where the first beam illuminates the ground. This is called as near range, and this goes till far range. This is the point nearest to the sensor is called as near range, and the point farthest to the sensor is called as far range. Yes. So in the same way, we have, like I told you, that the imaging takes place in the sensor moves in the azimuth direction and goes across the range. we have two resolutions, which is range resolution and azimuth resolution. So the range across track resolution has a formula which is c by 2b. So basically c is the speed of light and 2b is the bandwidth. So wider bandwidth means finer resolution. So if you need a very high resolution, means 0.5, less than 0.5 meter or less than 1 meter, your bandwidth should be very high. Accordingly, the along track resolution is basically limited to antenna length by 2 and roughly independent of the range. So whatever the antenna length is, upon 2 is the azimuth resolution that we had already discussed when we were differentiating between real aperture radar and synthetic aperture radar. And one of the key aspects of this sensor is polarization. So basically, the microwave pulses are transmitted in one polarization and received in one polarization. So here, if you see, this is the electric field and this is the magnetic field. E is electric field and B is the magnetic field. And the direction of propagation is basically Z. So if they move vertically, they are called as vertical polarization. And if they are propagating in a horizontal direction, if you consider with respect to Z-axis, they are called as horizontal direction. So basically, the blue lines signify vertical polarization, and the red lines, the red curve represents the horizontal polarization. So this is very important because we can have 4 combinations for a particular place when we are imaging. So if the transmit polarization is horizontal and you get a receive polarization, we get a HV image. If we transmit in vertical and receive in horizontal, we label it as VH image. If it is transmit in vertical and receive in vertical, it is VV image.